Hello everyone. So today's topic is neural networks, and we will follow with the introduction of artificial neural networks, what this technology is all about, and then we will see that what are the different and important components of artificial neural network architecture. So we will start the lecture today with the introduction of what these neural network architectures are. So as we know that neural networks, these are the parallel computing devices reflecting the computer model of the brain. So basically, the neural models, these were inspired by how the brain or the human brain works, and it actually uh, the main objective of these networks was to develop a system which can perform the computational task faster than the traditional system. Another thing that became the inspiration for development of these architecture was that scientists were trying to create the models that can imitate the working of the human brain. So how the human brain thinks, learns from the past experiences, and then accommodate its knowledge or its problem solving process, that uh, that kind of characteristics the scientists wanted to bring into the machines. So the computational tasks that need to be solved by neural networks are, for example, like the pattern recognition task. Then there are classification and approximation, optimization, and data clustering. So these are some certain application areas where neural networks uh, can be utilized to solve the different types of problems. So whether it is to classify the data into certain classes or categories, or for example approximation, finding out certain approximation to some problem, then optimizing some finding out the minimum or the maximum value for certain domains. So all of this can be done with the help of these architectures. As I already have said, that these models, they are basically uh, created by taking inspiration from the biological neural network. And so first of all, we will see that how the human brain is built up, and what are the basic unit of these biological neural networks. So when we see about the architecture of the biological neural network, it is composed of millions of biological neurons, and these neurons are the cells that are formed or that are arranged in a networked way. The cell is connected to other cells, and they are passing and processing information, and then passing it to the other neurons, the information which is processed by them. So as you can see that if we see the architecture of a basic you know biological neuron, the cell is going to have three different entities here. So these three components are, first of all, it has the soma, which is called as the cell body. So when we talk about the biological neuron, the soma or the cell body is responsible for processing the information. So whenever some input is being received by the neuron, that input is going to be processed here in this cell body, and then the input is traveling through this axon and reaching to the endpoints of the axon, where there are certain dot-like structures. So these dot-like structures, they are called as the synapses, and through these synapses, these synapses are basically work as the interconnection between the other neurons and this neuron or this neuronal cell, right? So we see that once the information reaches to here, then there are input end for the other neuron. So we can say that this is one neural cell, n1. Now this is another n2, this is n3, this is n4, and so on, right? So this way these synapses, they are interconnecting with the other, or interfacing with the other neurons, and based on that, the information of one neuron is going to be passed into the cell body or the soma of the next neuron. Now, there is another thing here, that's how this cell is actually receiving the input, because it has to process the input. So from where it is getting the input, so these thread-like structures here, this is called these are called as the dendrites, and they act as the receiver of the information. They receive the information from the environment or from other neural cells, and then pass it on to the soma or the cell body for further processing. So this way, the information being processed here then reaches to here as at the synapse, and then it is passed on to the next next neurons, or the interconnected neurons. So synapse, what is the use of these synapses here? So synapses are basically decides on the connection strength. So what is the connection strength? Based on that, how much information needs to be passed from one neuron to the other, that will be decided by this interconnection between the synapse and the endpoints of the dendrites. So based on that, the amount of information is going to pass from one neuron to the other neuron. So ANNs are also named as artificial neural systems. They are also called as parallel distributed processing system, and sometimes as connectionist systems. And ANNs have large collection of units that are called as the nodes or the neurons here. Nodes. So when I talk about ANN specifically means the artificial neural network, or artificial neural network model that we are going to study shortly. Now, the nodes and neurons, these are simple processors or simple processing units that operate in parallel. So one of the important or fascinating thing about the human brain is that it can efficiently process the information, because it is a parallel computing machine. So we can think of human brain as a parallel processor, which can process the input parallelly at different neural cell, and then giving you certain outcome or the decision for the inputs that have been perceived by your brain. So here also in the artificial neural networks, there are different types of nodes, which are called as the artificial neurons. So these are called as the artificial neurons. And all these neurons, they are connected or organized into some formation. We are going to see how many types of these formations or these structures or organizations exist practically for these type of networks. For now, we just need to understand that there are a collection of such neurons or such processors, simple processors with us, and every neuron is now connected to the other with the help of a link. And this link or the connection is between one neuron to the other neuron. So as you can see that every neuron is or can be connected to the other neuron in these set of neuron collection, and that way the information can be passed from one neuron to the other neuron. So this is one of the basic network architecture that we can see when we talk about the neural networks. And every connection here, which is represented as a link here, this link or this connection, it actually bears a quantity which is called as the weight, which is represented as W. So every link is going to have certain weight associated with it, and this weight actually suggests the strength or the importance or significance of this particular neural input. So we will see how this is going to impact the overall output of the network shortly. But right now we just need to remember that every neuron is connected with the other neuron with the help of a link, and every such link is going to have an associated weight with it. Okay, so if I number all these neurons, as for example, this is my xi, for example, this is x1, x2, x3 up to xi, for example. Now this weight I can represent as w1, this is w2, and so in the similar way we can assign certain numbering to these weights, so that we can understand that which weight is associated, or which weight represent which connection, or which link between two neurons. Now after this, we need to understand the utility of these weights, why these weights are used inside the network. So as we can see that weights, these are usually excites or inhibits the signal that is being communicated between two neurons. So once a neuron process the information which it has received, it is processing that information, and now whenever we are applying this weight with the connection, so this link is actually a medium from which this information processed here is passing from this node to this node, or from this neuron to the other neuron. Now how much information needs to be passed, that will be decided with the help of these weight quantities. So weight actually can triggers or can excite or can increase the processing value which has been processed by the previous neuron, or it can inhibit the signal also. So whatever signal is nothing but the information here, so please don't get confused here. The signal is nothing but the information which is being passed from this node to this node. We can say we are passing the information or passing the signal from one node to the other node. Now, each neuron has an internal state which is called as an activation signal or activation function, and we will shortly see that what we mean by these activation signals and why we use these activation functions inside the neural model. Then the output is going to be produced, and the output is nothing but the combination of the input signal and the activation rule. And once the output is generated for a specific neuron, that is going to be forwarded to the other units by using these links. So if I compare the artificial neural network model with the biological counterpart, I can see some analogies, and this slide represents the analogy between biological NN, and this column represent the artificial neural network. So the artificial NN and biological NN. So we can see that the processing unit inside a biological NN is the soma or the cell body. So this cell or the soma is responsible for which task? It is responsible for the task of processing. Then we have the dendrites in the biological neuron, and corresponding to that we have an input layer in the artificial neural network. So this layer or this component is actually responsible for receiving the input from the environment or from the other neurons. So we can say that the purpose of receiving input is being done by these two entities in the two different neural networks. And then we have the synapse. So synapse is represented or is being imitated with the help of the weights or the interconnection strengths in the artificial neural networks. And these weights, they are responsible on finding out whether the importance of whatever information has been processed by a specific neuron. So how much that processed information carries the weight. Is it more important or is it less important? So weight decide this thing, and thereby we can say that the weights are actually controlling the strength of the signal, that how much signal is going to pass from one neuron to the other neuron. The last component here is the axon in the biological neural network, and in the artificial neural network, it is the output layer. So as you can understand here, that this component is responsible for generating the output of the network or the output of the specific neuron here. Now, this is the artificial counterpart of the neural network, biological neural network. And as you can see that the model is graphically represented like this. And here the axis, these represent the inputs. And then every input is, passed to this node or this summer with the help of these connections. So these links or these edges or directed arrows, they are basically connecting the input or the input layer to this summation node, right? And every connection here is going to be associated with a specific weight value or a weight quantity. So you can see the first connection, which is between the first input value and or the first input vector and the summation node. Okay, this is given the weight value as W1, or is being represented with a weight value which is written as W1. The weight of the second input, I can also formulate it like this, that the weight of the second input is represented as W2, right? For X3, it will be W3. Then for Xn, it will be Wn. Now, all these, input and the weight, they are being fed to this summation, node. And now, whatever, sum is being generated from here, we say it as the net output. It is called as the net output. And net output is here denoted by Yn. So net output is just the sum of the products of these input and the corresponding weights. Once the net output is being generated by this summation node, activation function or a transfer function is applied here, and that converts this overall net input into the final output of the model, which is denoted by as Y, right? So from your inputs x1, x2, xm, we are creating the output Y by a mapping, and this mapping essentially uses two main things. Every input value, we are multiplying it with a corresponding weight or a weight vector. If your input is a vector, then W's will be vector that way. So every input we are multiplying with a corresponding weight. Then we are sending all these to a summation node, and this summation junction or the summation node is going to find out the sum of these products, and then we will be having one output which is called as net output, represented as Y in here. Now we apply certain activation function here. So activation function actually decides that how much input needs to be passed overall from this neuron to the other neuron. And it also be used for adding up the non-linearity to your model. So activation function, actually, whatever way you are placing, you can place a linear function here. So it can be, kind of a linear activation function. It could be a non-linear, activation function here, which we can use. So that way, the model can be converted into a linear, neural network based classifier or a regressor, or it could be like a, non-linear model that can deal with the non-linear data here. And finally, after applying the activation function, we are going to get some output which is called as the final output of the model. Now, the mathematical model of the previous graphical model is being represented here. So as you can see that how we are calculating the net input. So this is the net input we get here, net input, and we are multiplying the corresponding input with the corresponding weights, and then finally we are finding out the summation over there. So we are getting the net input like this. Now we are applying activation function here, and we will be getting our final output, which is denoted here as y hat, because it is the estimated output. So after seeing the basic, mathematical equation that works behind a neural network model, one more thing that I want to say here is that the model which we have discussed right now, that was called as the a perceptron model. Perceptron model. Perceptron model. And this model was given by the Rosenblatt. So sometimes we say that it is the Rosenblatt perceptron model, and a perceptron model could be a single layer perceptron. So we can have a single layer perceptron, or we can have a multi-layer perceptron. Multi-layer. The difference is just that in a single layer perceptron, we only have a single layer of input which is connected directly to the layer of the output. And in case of multi-layer perceptron model, we are arranging multiple layers which are having stacked neurons into it, and out of these layers, of course, in a multi-layer perceptron model, the number of layers must be greater than 2. So we are having at least an input layer here, an output layer here, and there are certain middle layers here, and these we can define by our own. So there could be a one middle single layer, there could be 2 layers in between the input and the output, and that way we say that all these architecture, they belong to the multi-layer perceptron category. We need to understand that these layers, apart from input and output, or those which are between these two, these are called as the hidden layers. These are called the hidden layers, right? So the basic perceptron model that we have seen, which generates certain output. Now we need to understand that what are the main components of an ANN. So when we talk about the main components, we can see that majorly we focus on 3 things. When we create a neural network, we focus on 3 things, and we decide on either the network topology, how the neurons, they are going to be organized, or how they are going to be arranged to form a network. The second important aspect or factor here is the learning algorithm or the learning rule, right? So this is again important in solving the problem, that which learning algorithm or which learning rule we need to use inside the network or the model. And the third important aspect here is called as the activation function used. So as I already have mentioned in the previous slide, that the activation function could be a linear one, it could be a non-linear one. Non-linear. So even if it is non-linear, then again there are variety of non-linear activation functions that are available. So which one to use for solving the given problem, that we need to decide. So the first parameter that we are going to briefly discuss is the network topology. So as you can see, the topology is the arrangement of the nodes inside a network. So how we are arranging the neurons in the form of a network, and how we are connecting them together, that decides the topology of the neural network. And according to the topology, all ANNs, they can be classified broadly into one of these classes. So we can have a feed forward network architecture, or we can have a feedback network architecture. So we can say that either I can create an ANN which is having a feed forward topology. The another variation is a feedback network consisting of feedback loops here. So when I talk about the feed forward network, feed forward, as the name suggests, that we are feeding in the forward direction, right? So when this type of network we are going to create, for example, like this. So we are arranging the neurons in the layers. Then we are creating the connections, and these connections are strictly in a unidirectional manner, or they are only in a forward direction only. So you can see that all the neurons of the previous layer, they are connected to the neurons in the next layer, but not vice versa. So layer 1 neurons can only be connected with a directed edge, or by a directed arrow to the next layer, or the layer 2. And the layer 2 neurons can only be connected in a forward direction to the layer 3 neurons. So like this, we can have the the connections here. So this type of network is called as a feed forward network. So this is kind of a feed forward network we have. The other type of network, these are called as the feedback network. So in a feedback network architecture, we are going to have feedback loops. So whenever we say about the loop, means we are connecting somehow the output of the final layer, which is called as the output layer, to back to the intermediate layers, or back to the input layer. Okay, so if that kind of architecture we are using, where we are feeding again the overall output of the model again back into the system, then those type of architectures are called as feedback networks. So if I draw a feedback network for you, first of all I need to label these layers. So this first layer is called as the input layer. Then we have the hidden layers here. So this becomes the hidden layer, and the final layer is always called as the output layer here. Okay, so with the same thing, we are creating a feedback network. So inside a feedback network, how we go, that we can go in 2 ways. Okay, what I can do, that apart from connecting these, right, apart from connecting these, I also can connect the output or the final output of the network, which is this, back to the system. So I can feed it like this way, right? So this is one feedback architecture that we can have with us. In another variation, what we can do, that we can connect the individual connections. So I can make these connections, or these individual arrows, or in these individual communication paths, as a bi-directional edge or arrow. So in that way, whenever this output, this neuron is going to generate certain output, that output is again being fed to the previous layer neuron, from which it has directly received the input. Okay, so that is another kind of architecture. So that is called as a fully feedback network. And the one which I have drawn here, where we are connecting the final output layer with the input layer, okay, this is called as the Jordan architecture or Jordan network. So these type are called as the Jordan networks. The next component that is important here is called as the learning algorithm. So as the name suggests, learning is an important aspect of the neural network, since they imitate the human brain functions. And as you can understand, that learning is the method by which the network refines or modifies over the past mistakes it has made while giving certain decision. So for example, if the previous decision was not that perfect, then it has to take certain learning from that previous decision, and it has to update its learning, not the learning, but it has to update the network quantities in some way, so that the next time whenever the same decision is going to be made up, now it is a improved decision. So not same type of mistakes the network is repeating again and again while processing the input patterns. So in learning, how we achieve the learning in the artificial neural networks, so this is just with the help of the modification of weights. So by modifying the weights, between the connections, the learning can be, can happen into these artificial neural networks. And if I talk about the types of learning, we have 3 different types of learning algorithms. The learning could be in a supervised mode, it could be in an unsupervised mode, or it could be in a reinforcement mode. The basic difference I'm going to discuss only in very brief here because of time constraints. So you can see in the supervised learning model, we are providing the input to the neural network. The neural network process the input, generate certain output, which is called as the Y, or the actual output of the network. Now, from here, we are seeing the desired output. So desired output is nothing but the labels which are provided with the input data set. So in the input data set, you have certain output recorded for those input patterns. And now you are calculating the error signal. So this error signal generator is doing nothing rather than comparing the actual output with the desired output. And if there is a difference between the actual output of the model and the desired one, then an error signal is going to be generated. So error signal is only represented as D minus Y, that the difference between the desired and the actual output. And this is again going to be fed up into the neural network. And neural network is learning to minimize this network error with the help of updation of weights. So weights are going to be updated, and in the next iteration, again certain output is going to be generated. Again, the output is going to be checked with the desired output, and this process is going to be repeated until the error is minimized. So this way, the supervised learning is going to work. Why we say that it is supervised? Because we are having desired output with us. So we already have that for which type of input, what kind of output needs to be there by the model. So we can always verify whatever output is being generated by the model with the help of this desired output that must be there. The second is called as the unsupervised learning. So as the name suggests, we do not have any kind of information about what kind of output needs to be generated. So whenever you pass on the input to the neural network, it generates certain output, which is called as actual output. And now you do not have any kind of help here. Okay, so what you can do best, that you can see the differences, or you can see the associations between different input patterns, and you try to group them into clusters. So this way the neural network is arranging the input into certain kind of clusters or groups by just following up the similarities into the input patterns. Now we have this is the reinforcement learning. So this learning is called as the third type of reinforcement learning. So in the reinforcement learning, we do not have the desired output, but we have certain reinforcement signal with us. And this reinforcement signal helps in guiding whether the learning is going into the correct direction or not. So, in a way, we do not have a direct, value of what kind of output needs to be there for this given input. But whenever it is making error, the reinforcement signal guiding the system that this is not the correct decision. Okay, it is not telling that how much difference is there in your actual output and the desired one, but it is saying that no, you are not correct. So that way, some sort of guiding signal is being given to the network that it needs to again adjust its weights and to achieve the final learning or the final output. And again, the reinforcement signal will be verifying whether the learning is going in a correct direction or not. So this is all about the learning algorithms that are being used. And then we talk about the activation functions. So as I already have said, that the activation functions help the neural network to use important information, and they suppress the irrelevant data points. So basically, your activation function decides whether the neuron should be activated or fired or not. So firing means that its output is going to be fed up to the next neuron with the full strength, and If it is not fired, means its output is not that significant, and in that case it is going to be suppressed. So this kind of functionality is being achieved in the ANN with the help of the activation function. I already have discussed that activation function could be linear or non-linear. So example of linear is where you can use a linear function, and for non-linear activation functions, we can have, for example, sigmoid function, or we can use a tanh function. So these are the most popular, non-linear activation functions that are most frequently used inside artificial neural network, which works with the non-linear inputs or data. So this is all for today. Thank you very much.